question, but in my humble opinion, the organizing has the best for class. To be the judge of that. So no pressure, thank you. So this is our opening speaker, Master Fishman from the Flatiron Institute, and we're talking about the ITensor library.
Thanks for the nice introduction, and thank you to the organizers for organizing such a nice conference. I'm going to be talking about the ITensor library, which is a tensor network library that's mostly used for quantum physics applications, but we're hoping to expand to other fields of applications. So let me get started. So the ITensor library is a library for implementing and running tensor network algorithms. And the basis for the library, which I think is the most unique part, is a labeled mode or index interface for tensor operations. So I'm going to be I use the terminology index for modes of a tensor. I'll try to use them interchangeably. I'm coming from a physics background, so there's a language barrier in some cases. So the idea is that the tensors we define, which we call ITensors, carry around labels on their modes, and we find this helps remove ambiguities in implementing tensor network algorithms. And the goal is to use the system to make it easier to implement tensor network algorithms on general graphs, which I'll discuss in this talk. And we have flexible and efficient implementations of various tensor operations, CPU and GPU backends, which we're still working on our GPU backends to make them more general, which I'll discuss. And the core of the library is basically dense and block sparse tensors. So block sparse tensors are something I think I haven't heard mentioned in the conference yet, but they show up a lot in our physics applications. And another interesting, unique aspect is I haven't heard the Julia language mentioned a single time in the whole conference. And we've ported our code, the ITensor library, from C++ to Julia starting in 2019, which has been a nice experience. And so now most of the development of the library is in Julia. So I'm coming from the Flatiron Institute in New York City. We're right by the Flatiron building up on the 9th and 10th floors. And I'm in the Center for Computational Quantum Physics. And the development of the ITensor library is based at the Flatiron Institute. And we have a team of software developers and postdocs who help develop the library. And we're often looking to hire postdocs, interns, software developers who are experts in tensor networks and high performance tensor operations. So to get started with the library, you could go to our website, itensor.org. We have a discussion forum where you can ask questions about how to use the software. It's itensor.discourse.group. And so let me just give you a basic idea for the tensor operation interface of ITensor. So you'd load ITensors, which is our Julia package, and you define, say, an index or mode dimension. I'm going to say it's dimension 2. I know that's a different limit from what people at this conference often think about, but for us, this dimension 2 might represent some local physical degree of freedom, like the state of a quantum particle, whether it's spin up or spin down, or whether it exists or not on a certain lattice site. But most of what I'll be talking about is not particular to any particular physics application. And so the first thing you do in ITensor is you define your indices or modes, and you define them with a dimension, and then internally they get assigned a random identifier which distinguishes them from each other. So we think about these as sets of local distinguishable Hilbert spaces. And so I'll define these modes, alpha, beta, gamma, sigma, kappa, and then we can build tensors from these modes. So we would make ITensors out of these indices. And the idea is that you define ITensors with indices, and if they have shared indices, that implies that there will be like an einsum contraction over those indices. And so these tensors A, B, C, and D, some of them have shared indices, and that the indices they share basically imply some graph structure of the graph connectivity of a tensor network. And we didn't give any extra structure to the indices, so these tensors will be made dense by default. And then if you want to actually go and contract the tensors together, we have this high level interface of using star as an operation for tensor contraction. And this is equivalent to like a traditional einsum notation where you would add the labels to your tensors for each tensor expression. And so the idea is that carrying the labels around with your tensors makes it so that it's easier to implement generic tensor network algorithms because you don't have to keep rewriting the labels over and over. And so, as I said, we're working on improving our GPU backend. So, for example, you can load the Julia CUDA package if you want to use an NVIDIA GPU, and you move your tensors, your ITensors to GPU using this generic coup function, and then you can perform the same tensor operations on GPU. And we're working on building out more GPU backends. So, for example, you could use Apple GPUs by just loading the Julia metal package, and a lot of this work has been done by a postdoc and software developer, Carl Pierce, who used to be in the Ed Palaev group. And so a common thing that we have are block sparse tensors. So block sparse tensors come about from symmetries of our quantum system. So if you're conserving some sort of particle or spin, you'll get a block sparse structure, which is basically that the tensors are symmetric under like a group action on the modes. I won't go into details about that, but basically block sparse tensors are really fundamental to most of the calculations that we do. And so the idea is that you just create your indices with some blocked dimension at the beginning, with some quantum numbers, which are basically like, say, the number of particles in your quantum system. And your graph becomes a directed graph because of contravariant and covariant indices. And then you can do the same operations that you were doing with dense tensors with block sparse tensors. So the idea is that the high level interface of making your ITensors and doing tensor operations should be agnostic about whether you're doing them on GPU, whether they're dense or sparse. And we are still under the development of like building out all of the GPU capabilities for block sparse tensors. And we're also doing a big rewrite of our backend to basically not only make ITensors work with GPU backends, but also just make the backend code more generic so that it's easier to incorporate new tensor types as backends to these high level operations. So some things we would like would be using better block sparse tensor formats, which we've heard about. Hopefully using some distributed tensor libraries in the backend. We haven't really investigated that directly, but it's something we have in mind as something we want to do. Say Cyclops or tiled array, using smarter systems for doing block sparse operations and other things like more advanced tensor symmetries. So I think there could be a lot of opportunities for collaboration. I'm going very slow. So the basic structure of the ITensor library is that in the backend you have some devices, you then have tensors with some sparsity structure, you have your high-level tensor operation interface, and then a new thing we're building out is basically that you then build on top of these tensor networks with various structures like a tensor train, or which we call matrix product states, MPS, tree tensor networks, hierarchical Tucker decompositions, and then more general tensor network structures like 2D tensor networks or even just generic tensor networks. And we would like device agnostic block sparse tensor operations to work efficiently for algorithms that are built for all of these tensor network structures. And so the core of the library is currently it's mostly focused on tensor train operations. We basically have like tensor train algebra and solvers. So we would have addition of tensor trains, contraction of tensor trains, eigensolvers and linear solvers for tensor trains. And most of these are solved with some kind of alternating least squares optimization. And these are basically the core of solving like a lot of physics problems, but these are really generic solvers for tensor trains that could be applied to other types of problems. And what we're building out now is generalizing our code from just being for tensor trains to other tensor network structures. And so then the goal would be to have solvers and tensor network algebra that works for these more general tensor network structures. But the code and the algorithms become more complicated, and we're building a new software package called ITensor networks to try to deal with that complexity. To give an idea for the ITensor network package, basically we would define our ITensors as we did before with the labeled modes, and then we would make an ITensor network out of those tensors, which basically keeps track of the graph structure of this tensor network in the background for you. And so then you can access tensors of this tensor network, contract them together, but then it allows you to do graph operations like asking for the neighbors of a tensor, getting a shortest path between two vertices, getting spanning trees, and computing contraction sequences, like optimal contraction sequences for how to do binary contractions of these tensors, which, as has been mentioned, is in general an NP hard problem, but there are nice heuristic algorithms for doing that. And so then our big goal now is to define all these tensor network algebra operations and solvers for general tensor network structures, not just tensor train. It's pretty easy to generalize all these to tree tensor networks, but then once you start adding loops to the networks, it becomes more challenging. And so what we really want are general algorithms for, like the core operations would be general algorithms for approximately contracting a general tensor network or taking gradients of tensor networks, which are essentially the core operations for then doing alternating least squares of tensor network and building tensor network solvers. And some things we would like to do are build like symbolic tensor engines to help us with automating certain tasks like parallelization or common subspace expression elimination or automatic differentiation. But that's just something that we're only in the process of thinking about. And so as part of this goal, we've already heard from Linjan in the morning, who mentioned a new algorithm that we worked on with Edgar and Miles Studenmeyer, who's a colleague of mine at CCQ, who is the original ITensor maintainer and developer, where basically you first take a tensor network, you split it up into partitions, and then you do approximate contractions of those partitions, approximating at each step the intermediates as tensor trains. So this is building. It's a new general tensor network approximation algorithm, and there's a few related algorithms, and this is, I think, a really important subproblem for this agenda of trying to build general tensor network solvers. And then another algorithm that we've investigating for general tensor network solvers is the belief propagation algorithm, which was originally developed for doing statistical inference. And basically it's a rank 1 approximation of the environment of a tensor network. And there's just this, you just iterate through these contractions of these message tensors which live on each edge of your tensor network. And this is a good, so this algorithm is exact on trees and accurate for tensor networks with small loop structures. For example, would be very accurate for approximately contracting a tensor ring, or what we call a periodic MPS. And we've been working on using this algorithm for implementing certain subproblems of tensor network algebra. For example, truncating a general tensor network, or applying quantum gates to a tensor network for performing time evolution. And so I'll just take a few more minutes to talk about an application of this belief propagation algorithm. So there was a recent experiment by IBM where they simulated the evolution of a spin model, and they used 127 qubits, which was a very big calculation, and they compared to state-of-the-art tensor network methods, and found that the tensor network methods couldn't keep up with the quantum calculation they performed. And so this was sort of, there was a lot of press about this work, saying that it was like a new era for quantum computing. And just to give you an idea for what calculation they ran, they had qubits that live on this lattice, so like they call it a heavy hexagon lattice, and they basically evolve it by this simplified model for spins. And so what we did was we took a tensor network that matched the graph structure of this of their quantum computer, and this is a nice application of the usefulness of having a tensor network library where you can just define tensor networks on arbitrary graphs and also contract them on arbitrary graphs. And it turns out that belief propagation is a good contraction algorithm for this application, because the loops are actually fairly big. So belief propagation is a good approximation. And we found that with belief propagation, we could basically match the results they got with their quantum computer. And it only takes, this fairly short page of code to define the tensor network on your graph, define some initial state, define the circuit that you want to run, and then run the circuit. So this was a nice initial application of the new software we're developing. So I'll just put up this slide as a conclusion that basically we want to, as a summary, build out these tensor network solvers for general graphs, and this will allow us to solve a lot of interesting problems like differential equations, quantum simulation, high dimensional integration, quantum chemistry. So yeah, that's the end.
Thank you very much. So are there any questions? I have two.
Like I think optimizing like tensor contraction is not trivial for me. Like equation like A is B C D E like that. Then how do you like generate an optimized code for like complicated general equations?
Yeah, there's basically like a growing list of algorithms for doing that. So I mean it's a big field, and I think there's probably, there's still a lot of open questions. Is that and be hard? So there's not going to be one perfect algorithm for every situation.
Like yeah, like did you apply some tiling for those equations?
Sorry, what do you mean
like
by that?
tiling, like blocking?
I'm not quite sure what you mean by
about
that.
algorithmic optimizations, like about like performance engineering, like if you like, how do you utilize like cache or memory? Because if tensors are pretty big, if you like run without any performance optimizations, then like you may not get very good performance because of like memory bandwidth limitation.
I'm not quite sure what in terms of caching, I think there's definitely some like a lot of work we could do in improving caching of intermediate tensors on it. I think that's where it would be important to have like a symbolic tensor engine, like we've heard about in other talks, like Ed Valev talked about that. So that's something that we only do in specialized algorithms, like for TensorTrain, where it's sort of obvious how to do the caching and also what the contraction sequences are, because it's a linear, graph. But for general graphs, I think it's sort of an open problem about the best way to do all of this. But I think having a symbolic tensor engine will help you sort of look at the global tensor network structure, find a contraction sequence, and then based on that contraction sequence, determine what kind of intermediate memory you need to allocate to reuse memory as much as possible. But it can be challenging because the tensors, if you go to approximate contraction algorithms, the size of the tensors and the block structure can be dynamic. So it's not obvious how to do the caching in a good way. So I think these are really important problems which we would like to tackle, and would be good to get help from computer scientists on those kinds of problems.
Go ahead. Like a comment that converse with your response to the levels. I mean, both are important. The caching you're talking about is about what intermediates you save or retrieve. He's talking about lower level optimizations at the level of filing loops and stuff like that.
Oh, I see. Yeah, that's a level where I would say we're not experts in that, like lower level tensor operations, and we're rolling our own data structures for block sparse tensors and not doing smart things with multi-threading over blocks, and we would like help with that. Yes, so you could imagine if you were trying to find an optimal contraction sequence, then you'd want to know something about like the block sparse structure, but that's a lot of information to feed up to a higher abstraction level. So finding the right abstractions where we can, not worry too much about all the details of the tensor would be nice, but yeah, if you really want to do the optimal thing in a certain situation, I think it could get really complicated.
Any other questions? What I wanted to ask is, what do you miss the most about C++, and what do you love the most about Julia? Yeah, that was a good answer, but I'll take yours too.
I guess the summary I give is that we found that it's been as fast as C++, like we've done benchmarks with their software,
Okay.
and it's just as fast. And we have a lot less code. It's a lot easier to develop in. There's a great package manager. Just the day-to-day of it is just easier.
Right.
Yeah. And I wouldn't really want to go back, I would say. So
So, I think we'll move on. Unless there's anything else in the question. I did. So I will move on to the next speaker. Okay, so our next speaker, Avery Laird, is coming from the University of Toronto, and I believe he's going to talk about the translation of Sparse code.
Yes. Okay, let me find my title slide. Okay, there we go. Set my timer to keep myself on track. So yeah, thank you for the introduction. My name's Avery. I'm from the University of Toronto. I don't know if there's any other Canadians here. Oh, okay, at least one. Great. So I'm a compilers person, mainly. So I come from the compilers world, and a lot of what I talk about will be stuff that seems totally obvious to a practitioner looking at code, but from the compiler level is actually an extremely hard problem. So the theme of the talk, I would say, is maybe bottom up or backwards or something like that. A lot of the things I'm going to talk about are going in reverse from the natural feeling of things. So first, I want to briefly talk about domain-specific languages. Even in the context of like tensor DSLs, there's a lot of them, and all of them have kind of different goals, different capabilities, excel in some areas and don't excel in others. And when I say domain-specific languages, I don't just mean Taco or something. I also even mean libraries, because you can consider high-performance libraries as a form of a DSL when you're using their API. So what it kind of looks like today, if you want to use a DSL, say you want to use Sparse or MKL or something, you have to use their API in that language in order to do it. So you can write all your code in that way, and then you decide later, okay, actually I needed to use this other accelerator. It's not supported by that DSL, or this DSL is old now, it's not maintained, now I need to find a new one. So you have to write in that DSL your computation every single time. So wouldn't it be great if you had some common representation? You can extract out those parts of the representation you want to offload to the DSL, and you never have to write a new DSL code ever again. So yeah, this common representation has been reinvented a million times over in compilers. So probably the most common one right now, most popular, is LLVM IR. But this is a very, like the IR used in a compiler is meant to be general, is by design not domain specific. So how can we use this kind of very, very general representation to extract out the parts that we want and offload those to high performance libraries or DSLs? So I'll use this motivating example to explain how everything works. I pulled this out of the CG loop inside of the NASA Parallel Benchmarks library, which is a very popular, well-known compilers benchmark. And yeah, so if anyone looks at this code, probably everyone in this room will immediately recognize this is a sparse matrix vector multiply using a sparse matrix stored using CSR. So the A matrix is sparse. What we've been working on is a tool we put in the middle there, Rev, where you give me this input code and we compile it to LLVM IR. And then you also give us the type of computation that you're looking for. And it should be kind of agnostic to any implementation detail. So if you think about an SPMV, what is an SPMV? It's really a matrix vector multiplication plus the added implementation detail of the compression is mixed in there with the code. So you give us this kind of detail agnostic code, and as long as it can get also into LLVM IR, we can work with it. So a lot of these examples here, these are all just written in like 2 or 3 loops of C, and as long as it compiles to LLVM IR, we can work with it. And so we take these two things, and my promise to you is I give you kind of a pair of information. So I say, okay, this input code you gave me, it's doing at a high level a matrix vector multiplication, and here's the format abstraction it's using, CSR and 2 dense one-dimensional vectors. And then what you can do with that information is give that to a separate module that will say, okay, a matrix vector multiplication plus CSR. That means, if I want to have Sparse code, then I should set up my tensors appropriately and then call the library. Similarly for MKL, it has a specialized CSR gemv call. You select that one and set up the proper code for code generation. So the first question I want to answer is, how do we extract this format information from the input code? Well, again, the theme is kind of trying to go backwards, because typically with DSLs, you start at the top level. You start with a separate definition of your computation and the storage format, and then the DSL compiler will mix them together for you and generate the code that you want. And we're trying to go the other way. You give us the mixed together code, we'll unmix it for you. That gives a bit of a hint about how we should proceed in terms of detecting the implementation details. So in the context of tensors, people have already proposed a general way to describe storage formats called format abstractions. And this is mostly pioneered by the Taco people. And they say, okay, there's a general way to describe all of these popular disparate formats out there that are all floating around. Here's an example of CSR. We have a sparse matrix at the top, and there's this tree, usually called like a coordinate hierarchy, and you can retrieve all of the non-zeros in your tensor by visiting this tree. So like on the far right, if I visit row 2, and then I go down, it has a child, two children on the left. At column 0 is U, and then at column 2 is V, yeah, and so on. And each level of this tree, you can have different ways of storing it. So for example, if you want to store it in what they call a dense representation, all you need is the size, because that you just have to, count up until you reach the size. But if you have something called a compressed level, then they say, okay, you can represent that using 2 arrays here, a position and a coordinate. And I don't necessarily have to explain all the details here to motivate the rest of the work, but what I will say is the coordinate array in this context is retrieving which column the non-zero was stored in, and the position array is telling you which subsequence of your values array to look for each row. So the main takeaway from this slide is mostly that you need to have these things if you want to have a CSR. That's the motivation here. And so then you can imagine what kind of code you'd need to travel through this tree structure. You'd need an iterator I that ranges between 0 to some constant. You'd need an iterator J that ranges between some values stored in the position array. And that iterator J will index into the coordinate arrays and the val arrays. And the perspective here is that this is like your necessary stuff you have to have for these kind of matrices. Sorry, these kind of codes traversing the tree. And then we can build a similar representation for our input code example. We have an iterator J, and it's ranging over 0 to some upper constant, and a K that's generated by the row array. And then some extra things here that weren't in the other tree, like Q, which is indexed by J, and P, that's indexed by this call array. Okay, so now what we can do is compare the two. Say, it becomes kind of like a unification problem. You just want to see, is there a possibility here I can map one to the other? So if you look at it, just kind of, visually, I'm just mostly showing, pretty pictures and not any technical results. But you can see that there is a way to rename these symbols so that what you have on the left, you can get on the right. So because the one on the left is dense plus compressed, and we decided, okay, we'll call that CSR. Then you can label those matching nodes here in the blue as CSR. And if you're assuming that these nodes are CSR, then you can also figure out, you can extrapolate what P and Q are. If I'm assuming this is CSR, then P and Q should be dense vectors as well. Okay. Yeah, and so you can generate these kind of these trees like mechanically. You don't have to do this by hand, and so you can take all these combinations of different levels and everything to generate all of these popular storage formats that people might use and matchers for them. And we could just keep running these matchers on the input code to try to find all different possibilities until we can't find any more. And then what we have is just a list of possible storage format abstractions that are being used in the code. Now, we have a candidate, but we have no guarantee it's correct. This step is basically just to prune out having to test every single possible combination of storage format and pointers in the code. So we've pruned out a lot of impossible matchings, but we still have to verify that it's correct. And then also we wanted to extract the idea of this like format agnostic code, and we still have formats in our code. So we can solve both of those problems by transforming the original code into another code based off the assumption we had about the format. So here we can create a new version of the code that has actually all dense vectors in it. Yeah. Then I'll rephrase, I'll say dense tensors. Okay. And then what we can do is try to prove that these two codes are equivalent under the assumptions that we made. And if we can prove that they're equivalent, then we get two things. One, we get the necessary conditions we need to check at runtime to make sure our transformation was correct. Also, we get a check that the assumption we've made makes sense. It's possible that these two codes are equivalent. Okay. So the way we do that, I just want to make sure I'm okay for time. Okay. The way we do that is transition systems, actually. So here's the inner loop of the example code. On the left-hand side is the input. On the right-hand side is the new transform code. And what I've shown is like a snapshot of a possible segment of the transition system for each code. So for the sparse code, we have some state processing some elements. And then what might happen is it will skip a 0. And so it will just keep going on the computation. When we look at the, I'll say dense version or affine version, we cannot skip any zeros. We have to process all of the elements. So there'll be an extra state there. And if we wanted to prove equivalence using the typical notion of like by simulation, for example, this would not be equivalent. But we can use, instead of branching by simulation, where we relate each state of together under like some certain conditions. So the case where they're synchronized, so to speak, where they're both processing the same element is fairly straightforward because you know that like AK, the original sparse version, it must be processing the same element as the dense one for them to be equal. And also the index that they're processing, so in this case, the column also has to be equal. Otherwise, these two states cannot be related. So that one's fairly straightforward. And then we will have these kind of skip states. These typically they're called like stuttering on the left-hand side. And under that condition, we just need to make sure that the new dense version of A is a 0, storing a 0. Okay, so we try to prove equivalence under this condition. We use a Z3 for that. So we use a SMT solver. So what falls out of that is the conditions we need to check at runtime to make sure this transformation was safe. So for example, there's an important property of the column index. It should be that it's strictly monotonically increasing. Like you can't have a column 0 and then a column 5 and then a column 4 and skip all the way around. Your column should be increasing. And actually this condition is something that falls out naturally from the equivalence proof. We can extract that as a runtime check. These facts are like known already. People have observed this about codes. So, you know, we could also look it up as in a lookup table, but this is just an interesting thing about the equivalence check. It's an extra thing we kind of get for free. Okay, so that gives us the format that we're using. The next part we'd have to do is figure out what is the actual kernel. When I say kernel, I mean a high-level computation that has nothing to do with the format. And what we do is actually we use equality saturation. So equality saturation is a fairly popular technique now, getting more popular. And I'll explain maybe just this slide and then kind of jump to the end because I don't want to take up too much more time. So what the idea between equality saturation is, you want to find, have an efficient term rewriting system. So you want to be able to place nodes that are in the same equivalence class together, and they can use, they can share between them other subtrees that may have been rewritten. So this is like the very common example to explain E-graphs that people will show. You can see that the shift left operator on the second graph, it shares the child of A and it shares the child of 1 there. And because the shift left and the multiply do the same, they're equivalent, we put them in the same equivalence class here shown by levels. So I won't explain the rest, but the way we check equivalence is through a series of rewrite rules that we apply. Okay. So I'll skip that part. And I'll just show the last slide here. I don't expect that, to impress anybody by speed up. The speed up should be, obvious. Of course, you'll beat any other code there. The thing I mostly want to show here is about the overhead of the runtime check, because people will often ask, okay, but now you have to run all these checks at runtime to make sure that the input data satisfies some constraints. Won't that take up a lot of time? And here we have some results. The right-hand side, most one, the netlib-C, is actually a Fortran, and the other two are C, sequential C. And at most, the runtime check overhead is about 7.9% of the optimized runtime. Yeah, I think that was the last thing I wanted to say about that slide. Okay, and before I finish up, I just wanted to mention that I am in the process of writing this up right now. So please come up afterwards to me with any criticisms, attacks, or whatever, so I can make the paper better. Okay, thank you.
Compiler takes off, and the compiler will have a lot of questions, but we're going to do this for that. So anybody else have any questions? Right.
So I was kind of wondering, so the input is a description of the SPMV in this kind of loop format to your program, from which you kind of infer it's an SPMV and you map it to a function. Am I getting the workflow of that correct?
So the input, the kind of specification is meant to be quite general. So like when I'm doing these benchmarks and I want to match like a GEMV, I'll just write like, I'll just write 2 C for loops and that's it. Yeah.
Okay, and then it automatically, so is this kind of robust to if I modify the code a little bit, if I were to do some kind of performance optimization?
Yes.
Does this sort of account for that?
Yeah, great question. So that's addressed in the, where do I have it? In the equality saturation part. So we have a bunch of rewrite rules, for example, loop interchange, tiling, all that kind of thing. So it can do some de-optimization. It's not like crazy. Like I'm sure people can write a code that will not be able to be mapped back, but it is designed to be able to be robust in terms of those kind of common optimizations, fission, fusion, that kind of thing. Yeah.
Thank you for your presentation. I have a question. Have you considered using MLIR? Because like in MLIR, there's a sparse side, like, and like
Yes.
all these rewriting rules and all these like semantic extraction would be much easier.
So that's a great question. MLIR is still dependent on the front end. The front end will only give you so much information. So you still need a tool like this. So like I envision, I haven't done it yet, but my plan is to also have MLIR as a backend. Because you still need to have a tool like this as an intermediary to do the analysis. Yeah, MLIR will not do the analysis for you, but it will, I think it's a great candidate for a backend. Yeah.
I'm just trying to understand the usability of this. So typically in today's job, I use Numba to express a vectorizable code. And in my code, and Numba takes care of everything, right? Like,
Yes.
so in this case, I know where the vectorized code is there, so I'm able to express. So in your tool, if the people who don't know to write the vectorized code, they know classical writing, then it's going to help them to extract it. Is that the
Yes.
way we have to understand it?
Yeah, so a big motivation for this is trying to examine legacy code. Yeah, so a lot of legacy codes will have this kind of thing written by hand. But if you're already using a very high level representation, it's harder to convince people that it will be useful. Yeah.
Just to make sure I understood it and to translate to your question, I think this kind of work is really challenging and really important and interesting. But what I see it as is you have these codes where you have these written, but maybe you want it to be substituted by a highly tuned library implementation. So essentially, it's a kernel matching problem. That is, you look at something that's written by the user and you recognize and then say, oh, this is exactly the same thing as what is available as a library function. And so over time, this various compilers have tried some syntactic pattern matching, and there have also been several efforts that have tried to use semantics.
Yes.
But still, there isn't really any existing out-of-the-box solution that anybody can use for this purpose. And so this is really interesting work.
Oh, thank you.
Thank you.
Any other questions?
Yes.
So you use the solver to be
Yes. Yes. So what we initially did was we treated the whole loop nest as a transition system. But then this new technique is something we settled on, where we actually traverse the loop nest inner to outer. We treat each subloop as actually like a functional fold. So on this slide, we try to translate the subloop into a functional fold over a pure function. And then the transition system for such a code is always going to be the same. And actually, as long as you have a loop where the domain is not altered inside the loop itself, you can always describe it as this kind of fold. And so that helped a lot for the transition system. Then basically all you have is an index variable that's increasing, and you have a state that you modify each time. So the checking becomes like super simple, and the solvers are quite good at it. Yeah. Thanks.
Coming to us from University of California, Berkeley, and he will be talking about butterfly factorization of tensors in parallel.
Great. Thank you very much. So I hope we've all been having a good time learning about sparse tensors. I'm going to devote almost the entirety of this talk to talking about dense matrices. So, you're definitely getting what you signed up for here at the Sparse Tensor Workshop. So, but in my defense, what's basically going to happen is the algorithm that I'm going to be discussing was developed first for matrices, and so I'm going to explain it in terms of matrices, and then we'll see how it generalizes to the tensor case toward the end, and we'll look at some results, and it will all be tensory and fine. So this is joint work with Yang Liu at LBL, with Tianyi Shi, who is right here, but normally is also at LBL, and with Hungary and Zhenlong as well at their various institutions. So we enjoy factoring low rank matrices as a way to compress them, but some matrices, such as the matrices that you get from a discrete Fourier transform, are not low rank, but they have submatrices that are low rank and that obey various hierarchical or non-hierarchical properties. Butterfly factorizations can factor these matrices. Our contribution is to extend butterfly factorizations from matrices with low rank submatrices to tensors with low rank subtensors, where the definition of low rank in the tensor case is in our case that if you unfold this thing into a matrix and factorize it, then you get a low rank matrix. So let's talk about how you do a butterfly factorization in the matrix case and why this is exciting. So a matrix A satisfies this complementary low rank property or CLR property if for any sufficiently small submatrix, any way that you want to carve it up, that submatrix is low rank. So in particular, you're going to have this constant C that doesn't change with n, and that gives you this upper bound on the number of elements that you need to have a low rank submatrix. Now, this is kind of a very weak property in that it doesn't say much about the hierarchy of the matrix. If you're used to like higher order off diagonal low rank matrices, then there's nothing like that going on here. But it's also a very strong property because it really doesn't care how you split up your matrix. So if we have a matrix split up this way, say how we've got it on the left, with lots of very long, thin matrices, then all of these are low rank. Or you can split it up the other way and have tall, narrow matrices. All of these are low rank. You can sort of do both at once. All of these are guaranteed to be low rank. So you can get a lot of different grids, and if you split your matrix up along any one of those grids, you get low rank submatrices. Now, some of you are probably thinking, what's the big deal? We've already got, by this property, we have, say, this set of submatrices, they're all low rank, so split your matrix up like that, factor each of them, mush the results back together, you've got a factorization of your matrix, job's done, and you can all go home. The problem with that is that as soon as you commit to just naively factoring in this way, you're giving up on all the possible factorization that you can get out of this way of carving up your matrix. And if you factor it this way, you're giving up on this, say. The complementary low rank property gives you a lot of different ways of splitting up your matrix. And what we really want is some kind of method that will allow us to take advantage of all of them. And we can imagine how this complementary low rank property generalizes to tensors. Again, if all you need is to say, you split up your tensor along most of the dimensions, along all the dimensions, and as long as your subtensor has sufficiently few elements in it, then you are going to have a low rank subtensor which can be contracted. So let's talk about how we actually do go on and contract these matrices. The big idea is that you start by doing the thing I just said you shouldn't do. You start by by splitting up your matrix horizontally, say like so. There are a ton of variants of this. I'm just going to pick one to focus on. You start by splitting up your matrix horizontally. You factor each of the horizontal submatrices. And then you take your factored horizontal submatrices, you merge the adjacent horizontal ones, and you split them in half vertically. And in a minute, I'll have another diagram that's going to explain this in more detail. This is just a bit vaguer to start with. But if you look at just this structure for these matrices, and you merge the adjacent horizontal pairs, and then you split them in half vertically, what you get is this central structure for the submatrices. And then if you merge adjacent horizontal pairs here and split them in half vertically, you get this on the right-hand side. So by continually merging, factoring, splitting, repeating, you can go through every possible way of splitting up your matrix. So what that looks like in practice is something like this giant diagram, which is just marvelous, isn't it? So we start over in the top left corner here. You split up your matrix, and then you factor each of these four matrices individually. And then you want to combine these things back into two large matrices that together give a full factorization of your original matrix. And that turns out to look like this. And if you just do out the matrix multiplication, you'll see that that's how it has to be. But hold on a minute. This matrix up here, which is partly hidden by the zoom thing, I think, this matrix up here has the exact same structure as this matrix that we started with. So we can actually say, all right, we've done all the factoring we can, having split up our matrix horizontally. But we can use this as a pretty good proxy for our original matrix, and we can see what happens if we split this up another way. So we're going to merge adjacent horizontal submatrices of this thing. We're going to split vertically, and we get this. And all that we've done here is we've just rearranged the boundaries between submatrices of this matrix on the right-hand side. And then each of these four things, by the same complementary low rank property, each of these four things is guaranteed to be low rank. And so we can factor them, like so. And then it turns out that there's a way of putting all these four back together into a set of big matrices that together multiply to give you the whole matrix back. And it looks like this. So these four vertical blocks here go into this matrix down here, and then the horizontal blocks go into this matrix here. But wait a minute, Michael, you say. Our previous logic has relied on asserting that we always get basically the same matrix structure on the right-hand side. And this looks nothing like this matrix. We've got a different matrix structure now, but hold on. Because all that we actually need to be able to do, remember, is merge horizontally and split vertically. And we've got horizontally adjacent, like horizontally stacked blocks here next to each other. So we can just go right ahead and merge those. This is close enough to the structure of this that we can do everything we actually wanted to do with it. So we merge these things horizontally, we split them vertically, we factor them, and I've skipped that stage because there's no room on the slide, but when the dust clears, we get this. And now we have everything on the right-hand side is just pure block diagonal, and there's no more to merge, there's no more to split, there's no more to factor, and we are done. And we have now factored every possible arrangement of grids on this matrix, and we have a fully factored, butterfly factored, complementary low rank matrix. Can I get an amen? Tough crowd. So the immediate question now is, how do we turn this into a tensor thing? So splitting and merging of tensors translates directly. You just rip your tensor apart along any dimension you like, smash it back together, you're good to go. Factoring also translates more or less directly. The way that you do it in butterfly land is you take your subtensor, you unfold it into a matrix along one axis, you factor that, and then you refold it and you get a matrix times a tensor. If you've done Tucker decompositions, it's going to be very familiar to you. What's a little bit trickier is the idea of the diagonalization and the recombine. So if we look back at this last slide, then we see that we get these very bizarre shaped matrices in the middle. Now, the reason why this is tricky is that, you know, if we start off, we have these diagonal matrices, and it turns out that the diagonalizing, like putting matrices in a block diagonal format, does translate directly to the world of tensors. But that's because we start by really only splitting along one axis, one dimension. Whereas down here, we're splitting along two separate dimensions. And once we are in tensor world, we have 3, 4, 5 extra dimensions to worry about, and we want to split along more than one dimension at a time, then it doesn't become clear how we'd reassemble something like this into just a set of tensors that will all multiply together back into a tensor network to make the big tensor that we want. So this is something of a problem, and it's not clear how we draw the analogy between the matrix case and the tensor case. Which is why I have given you the same slide again, but now with lots of circles on it. Because the point I want to make here is that while these structures can seem very strange, they actually obey a very strict binary tree law. And the fact that it's a binary tree, incidentally, is negotiable. In fact, if you want to split along more than one axis and factor along more than one axis at a time, you can use more complicated trees, but because this is just matrices, it's got to be a binary tree. the way that you can look at it is over here, we start by factoring all the columns at once. So every factorization that we have considers all the columns of this matrix. And so we can associate all of the results of this factorization, all of these matrices, with the root of the tree, which is associated with all the columns of our matrix. The second phase involves splitting the columns of the matrix in half. And now if you look through the rest of the factorization, these sets of columns never interact again. What's on the left over here and what's on the right over here, they're now matrices that are basically being factored completely separately. The title of my talk promised in parallel. This is where that comes in. You can just farm these out to totally different computers and they can just do it. They don't have to talk to each other ever. And so we get this structure, this tree structure down here. And then if you look carefully, you'll see that in fact, within each node of the tree, all that you have is a diagonal matrix. And suddenly these intermediate matrix structures seem a lot more tractable. They translate a lot better to tensor world. And then if you carry on this tree structure, and again, you split like so, every time you split every set of columns in half, and that gives you your two children. Then down here again, all that we have within every tree node, all that we have are block diagonal matrices. And toward the end, each block diagonal matrix is just dense. It's got a single block, but still technically block diagonal. And then at the end, we just have this final block diagonal matrix. And so all of these things generalize directly to tensors. And what you do now is you just have to write a custom matvec routine that, rather than consuming a list of these matrices, consumes one of these tree structures with block diagonal matrices at every node, and it knows how to split your vector that you're trying to do your matvec with, and apply the relevant block diagonal matrices at the relevant points of the tree. And you can just do that if you work out how to do the matrix multiplication. Then there's nothing special about this. You just do the matrix multiplication and translate that to the tree. And then from that, you can just implement the tensor algorithm directly. So we have some results here to show that we actually did do this and that it works. Very exciting. The tensor that we use here comes from a Green's function. So the idea that we had is you have two parallel plates held a distance 1 apart. And so you have this 4-axis tensor, x, y coordinates on one plate, x and y coordinates on the other. And between the 2 points on the plate, there is a force determined by this Green's function down here, which is highly oscillatory and a very good candidate for butterfly factorization. Now, normally when you have a tensor like this, the way that you factor it is that you unfold one plate into one axis, just one long n squared length axis, and the other plate gets unfolded into another n squared length axis. And so you get an n squared by n squared matrix, and you factor that. Problem with that is that when you do the unfolding in space, you're introducing spatial discontinuities because there are going to be points that are close together in space, but that are quite far apart from each other in terms of the matrix. So you're introducing artificial discontinuities, you're raising the rank, that's bad. And so you see that we get, like, this is the matrix factorization, we get a worse pre-constant even down here for very small n. The tensor, on the other hand, is able to respect all spatial closeness and take advantage of all of that. And so we get both a better result for small n and even a better order of growth. So this is pretty cool. In conclusion, we have this better order of growth, this better time. Future work, we'd like to explore some even higher dimensional tensors. We've been working with 4 dimensions, 6 dimensions, see if we can push it to even higher dimensions. We'd like to test on a wider array of tensors. We've just been focusing on this Green's function, but there are many other tensors that are amenable to this kind of thing. And we'd like to consider some variants to our algorithm, which can achieve even better performance in cases when you have even more structure. Say if your kernel is translation invariant, then you get a lot of diagonal looking things in the tensor. And so there are ways of compressing even more with that. Thank you very much to Yang, who advised this, Paul Beckman and Tianyi Shi, who helped with it and worked together with me on it, and NSF, who funded it. And here's the reference for where we are at with matrix butterfly factorization, if you're interested in that. That's all I got. Thank you very much.
You mentioned the complementary low rank property. So what kind of problems have that? I'm sorry, I missed the definition of that.
No. Great question. Great question. So this Green's function thing has it. A lot of highly oscillatory kernels have it. So if I can go all the way back through this to this, this thing. So the idea with an intuition for why lots of highly oscillatory kernels have it is that if you have a highly oscillatory thing, then up here along one axis, you have some waves. And then down the side here, you also have some waves. And then in the middle, they interfere with each other. And so the idea is if you restrain either one or the other dimension, then you're going to reduce the amount of waves that can interfere. Like you'll have a lot of waves here, but then very little to interfere with them down this axis. And so you won't get a lot of weird behavior just within this submatrix. Lots of highly oscillatory stuff has it. This was originally developed in the context of the discrete Fourier transform. The discrete Fourier transform matrix doesn't just have this numerically, it provably has this property. And the proof is you can do a fast Fourier transform. A fast Fourier transform is simply a matvec by a butterfly compressed discrete Fourier transform matrix. So that's pretty cool.
So when it comes to CLR, can you split the matrix in a non-uniform way to take advantage of some weird structure of the matrix, or do they need to be symmetric like that?
Yeah, great question. That depends on your definition. There are variant definitions of CLR. Some require that you split it up along a grid. Others require that others just say any sufficiently small submatrix placed anywhere. Most of them say it has to be contiguous. In fact, I think all of them say it has to be contiguous. There are various definitions. I think most of them apply to most matrices. In practice, you always want to use the grid because it makes your algorithm more general.
Oh yeah, thank you for explaining butterfly to slow people like me. But it seems very similar actually now that I'm to H matrices, at least in the dyadic case. What's the relationship between this and H matrices? Algebraic FMM, there are lots of names for basically very similar concepts.
If you tell me what those are after the conference, I'd be happy to discuss it with you.
Oh, thank you. I'm just curious about just 2D case. If you partition the matrix into vertically, then each partition, the rank of each partition the rank can be 1. But if you partition the matrix in horizontally, then the rank of each partition can be much larger than 1, right? In some extreme cases.
So forgive me if this doesn't quite answer your question, but the fun of the complementary low rank property is that no matter which way you partition it, as long as you partition it into sufficiently small chunks, you're guaranteed not to have a large rank. Now, that doesn't guarantee that your rank is always the same. In fact, it very rarely is, but there is a bound, and it's a pretty nice bound. Like in my experience, I've seen you have size 24, size 30 matrices, so submatrices, and then these have rank 12, rank 13, and then that rank doesn't really increase as you partition it a different way. So that's the fun of complementary low rank. Of course, this doesn't hold for matrices in general.
Because I was wondering if the way to the direction of the partition, the first partition is not correct. I thought in some extreme cases, all the informations can be, lost, right? Lost. Like suppose you partition the matrix into just 1 by 1, but if this rank is not 1, then when you factorize that matrix, then the factorization may they have a lot of errors like that.
Yes, so that's why here we have this small constant c, and that's why I said that they need to be sufficiently small. In practice, figuring out what c is something that you do by setting it as a knob and twiddling it back and forth until you get good results. I tend to use c as either 8 or 16. That's because I feel like it.
Oh, thanks.
Yeah, I have a comment about the H matrix question. So basically, if you have H matrix or H2, it's like off diagonal things, but CLR doesn't require it to be up, only low rank off diagonal. So this is like different from a hierarchical matrix, but like similar in some way.
Hi, pretty basic question, I think. Does the order matter in which you do the split for the factorization, or are they equivalent?
By order, do you mean like, does it matter if you factor the top one first or the bottom one first or something?
No, I mean, like, does it matter if we do the split horizontally then vertically and then using the square grid? Or if we can
So
figure
the
that out?
algorithm that I showed you here
Mhm.
does rely on a specific order,
Mhm.
and it turns out that it's much easier to build your data structures. But in theory, I think you could probably cut it up any way you liked. It would just be look, the thing about this algorithm is that it's already enough of a hassle to implement. You have multiple trees, some living within each other. If you want to parallelize it, which you do, you have a ton of different factorizations taking place on different cores. In theory, you could do that kind of thing. In practice, I'd say it's pretty much always more trouble than it's worth. And you're always going to be doing the same factorizations anyway. Although if there is theory on this, Tianyi would know more than I would.
Sounds like something after the talk. Anybody else? Let's make a quick one so we can proceed. No? All right. So Mit, I think you're going to be our last speaker. So Mit Kotak comes to us from MIT, and he will be talking about optimizing, I understand, dot products and some symmetry in neural networks. And he's setting up his laptop right now. Okay. Yeah, something's happening.
No, I think I should be good. Okay. Cool. Let me time myself as well, since I'm the one stopping you from going back home. So, go ahead. So yeah. Hey guys. I'm Nick. Unfortunately, so yeah, I'm first year. Sorry. So yeah, I'm a first year grad student at MIT. And I work on Equivariant neural networks, and we have like a big tensor product problem. So I want to try to give you guys like the minimum amount of, I guess, problem motivation so that like you can help me solve this problem. So like the way this talk is going to be structured is that I'm going to like for 10 to 12 minutes, I'm going to just talk about like equivariant neural networks. And then at the end, I'll just give you like enough of a teaser that, hey, like this is the tensor product, this is the tensor contraction, and then we can like talk offline. Cool. All right. And then, yeah, I'll let me explain these three pretty pictures. So the first one is like just the data types that we deal with. So rabbits are a good way of explaining that. And then the middle one is the outer product of the tensor product that we do. And then the last one is just like using these like equivariant models to like featureize geometry, which is what we are in the business of sort of doing. But yeah, and yeah, I would definitely would want to thank the organizers of this workshop. This is a really cool opportunity. And yeah, this work is funded by NSF and DOE. So yeah, let's get started. And also, so yeah, I would like to acknowledge all of my collaborators at MIT. We call ourselves the atomic architects, spherical cows because physicists. But yeah, yeah. So okay, so the problem motivation is that we have physical systems, in our case, atomistic molecules and stuff. And let's say we have like a benzene molecule here, And then whenever you want to describe like molecules, you need like a coordinate system. And then the thing with coordinate systems is that like your choice of coordinate systems are pretty arbitrary. Like you can describe the same system using different coordinate systems. And now you might, and often you can convert between different coordinate systems using like Euclidean symmetry, which is rotation, translation, and inversion. And now you might be like, okay, but why is that an issue? So it turns out for machine learning models, these two guys, 1 and 2, are separate systems until you like explicitly train your machine learning model on like all possible configurations, which is kind of annoying. So the thing that we want to do is that, can your machine learning model somehow like learn like all of this symmetry, like even without like looking at the data? Like, is there a way to just like formally guarantee certain symmetric operations inside a machine learning model so that it can spend its precious weights on the information and not the coordinate system? Okay, cool. And one other thing that I guess I would want to clarify is that there's like 2 ways of solving this problem. There's invariance and then there's equivariance. So for this benzene molecule problem, you could just be like, let's just skip the distances. Let's just focus on like maybe the angle, because that's kind of like an invariant property. And that's fine. Like you can use invariant features to describe your systems, and that's completely fine. What I would like to focus on is equivariance, where somehow the coordinate system is baked into the machine learning model. And as your inputs change, your outputs will also change. And now you might just be like, okay, but like, sure, like theoretically it makes sense, but like, has it been applied? And sure, it has been. So yeah, it's been used for like state-of-the-art molecular dynamic simulations. So like if you're like material sciencey, then like all of these applications would make sense. But because this is like, I guess, a sparse tensor crowd, my personal favorite is this one. So this is the 2023 Gordon Bell nomination. And they were able to simulate like a HIV capsid molecule, like 100 million atoms on like 1,000 GPUs. And they used equivariant neural networks. So that's pretty cool. All right. And then just to, I guess, give you a contrast between invariance and equivariance, why we would want to focus on equivariance is because of this beautiful plot. And for like, I guess, just to give you a summary of how, like why this makes sense. So in machine learning, we like to focus on like data efficiency. So like how fast can your machine learning model learn the data? And here you can see that, so on the y-axis, you have the error, and on the x-axis, you have like the number of training samples. And with equivariant models, we have seen that it's not only more accurate, but it also learns the data faster. And here's one other neat trick why we like playing with higher tensors. So as you go to, I'll explain what L means, but you can just think of like L equals 3 as like a really high order tensor, like a really high order symmetric object, if that makes sense. So I'll talk more about it later. But as you can see, as we go to like higher and higher tensors, it's following like a power law curve, which is really cool. So like theoretically at like L equals 7, you might just be at like the end of this thing, which since all of us are like broke academics who don't have like 1,000 GPUs, this is pretty cool. All right. So yeah. So now let me explain like the 3 features that I was talking about. So I'll talk about the data, what kind of data types we play with, how we interact with them, which is where the sort of computational complexity comes in, and then just briefly talk about like how we actually use this in like practice. Okay. So yeah. So the way equivariant neural networks sort of take in data types is using these things known as irreps, or irreducible representations. And like the neat thing about irreducible representations is that they have like 2 properties. One is the angular frequency, and then other is the parity. And like, since I'm talking at a really abstract level, I thought let's just look at some examples. So like, for example, for L equals 0, the even parity would be like just simple classification. So just a rabbit. And then for the odd parity, we will have something that is similar to chirality or handedness, right? So a left hand and a right hand. And now when we go to L equals 1, we'll get our favorite vectors, which is what we have here. And then the even parity here would be rotation, right? And similarly, you can keep on playing this for like higher and higher orders. So for L equals 2, we have a double-headed ray. So for example, if you have like a time varying electric field where with a double-headed ray, it is unaware about like the x-axis. So it treats the plus x and the minus x as like the same thing. So if you have like some form of electric or magnetic field, then this is a kind of data type that you would want to be playing with. And then for odd parity, we have like the helix, which I guess like people who work with DNA might be familiar with that. And like with the helix as well, if you look at it from the top, it's different from when you look at it from the bottom. So that's kind of like the handedness, if that makes sense. Okay. And then the reason why we like to work with irreducible representations is because any sort of data that you have can be mapped onto this irreducible representations. So it's like the smallest vector space that you would need to represent any form of data, if that makes sense. And again, I'll give you more and more intuition as we go forward about this. But okay, so those are the data types. Now let's talk about the main reason why we are here at this conference, right? Tensor products. So just to give you an example, when you're working with two scalars, when you do a tensor product between two scalars, you get a scalar. If you tensor product a scalar with a vector, you get a vector, which is like might be slightly elongated or shrunk. And then when you do a tensor product between two vectors, you get this thing which does not have like a clear angular frequency, right? Like this was L equals 0, this was L equals 1, but this one is a bit different, right? So what we can do with these things through the magic of group theory is we can decompose that into like smaller irreps, if that makes sense. So in this case, this can be decomposed into a dot product, which is the trace, the cross product, which is like the antisymmetric component, and then this last thing, which is like the symmetric traceless thing. And the point that I want to emphasize here is that you were playing with low order tensors, but you were somehow getting access to these like higher order objects, which is why, so to help you get some intuition for why these neural networks are like really efficient, they're able to sort of work with like a very compressed form of information, if that makes sense. And yeah, just to talk some shop. So because this is an outer product, it is like very much not scalable. And this is how the Einstein summation also looks. And this one has like a OL cube complexity. And this is not even like the full picture. So in practice, because you like in machine learning, you're working with like multiple channels, right? So in practice, actually, when we are like working with like, let's say transformers or something, the actual complexity is actually OL6. And since I don't have the time to go through the math, you can just reference that thing. But so this is bad, like this is very bad. And we'll revisit this again, how you can help me solve this problem. But yeah, just to talk about how we use these sort of tensor products and data types in practice. So let's say you have like 2 point masses here. So our neural network would take in like your geometry, which in this case would be like just like the coordinates of like the 2 masses, and then some features. So this can be, I guess, mass, velocity, acceleration, and so on, right? And now you might ask, okay, how do I use your library or like your neural networks to sort of capture this information? So the way we can capture this information is, so for the mass, because mass is just a scalar, we can use like the L equals 0 data types, and then since velocity and acceleration are vectors, we can use like the 1O data type. And then the way you would just plug it into the model. So we have like a whole library that just deals with all of these tensor products and all of this group theory back of the envelope thing that we need to do. So you can just, this is how you would like express this in our neural network. And yeah, just to like make sure that this is very clear. So yeah, this is how we play with all of the data types. And then finally, I guess, let's just revisit the tensor product, like talk more about like what the exact structure looks like. So if you remember the Einstein summation that I showed you before, it can be written as like this thing. And since this is a sparse tensor workshop, the opportunity that we have here is this last thing. So the way, so like, and just to connect it back to like the data types that we had, the dense guys are the two sort of input vectors that you're taking in, and this sparse sort of three-dimensional tensor that you have here is like the coefficient matrix that helps you interact, that helps these two irrep objects like sort of interact and like makes sure that you are like, if you go into like some higher dimensional space, you can still bring it back to like vectors. And since, so at MIT, we have this thing called mens et manus, where you wanna show people rather than tell them. So I'm gonna try actually showing you how these sparse matrices look. So this is, and again, like you can like offline, you can tell me how I can sort of represent this thing better, because right now we're just doing like dense matrix multiplication. And as you can see, the sparse tensor has like some form of sort of spatial sparsity, but it, like the thing is that at every L, the structure slightly changes. So we are looking at this one. Just to, yeah. So the X, Y, Z dimension. Yes. So this is, yeah. So this is, so the X and Y in this case would be like the I and J sort of dimensions. And then, yeah, K contraction. So this is just showing you like the sparse thing, because the dense thing can be like anything, like that's the input. But this is something that comes from like the group theory sort of formulations that we have. And like the problem that we have is that this thing is too big to fit onto the GPU. So we hopefully need to come up with like some form of, yeah, go for it. So it's going from -1 to 1, because that's what just the coefficient matrix looks like. Yeah, these are just like coefficients. So like, yeah. And the nice thing is that these things, like they're completely independent from the data that you give in. So we actually just like pre-compute them. And then the only problem that we have is that this guy is so big that it does not fit onto the GPU. So technically this whole operation can happen in like one kernel call, if you're just smart with how we are like, I guess, storing the data. Yeah, sure. So this one, if you look at like a L equals 6 thing, then I think this can go to like 2 or 3 gigabytes, like, which, yeah. Yeah. I mean, I want to simulate 1,000 million atoms, hopefully. It's kind of the problem that happens. So, and again, I can like talk more about like the exact sparsity, I guess, of how this looks. So that's why, like, just wanted to show you this, and then offline we can like completely geek out. But yeah, just to like sort of leave the talk with like the open questions that I'm investigating. So the first one is that because we use this tensor product in like different machine learning applications, is there a way to come up with like different schedules of like, because sometimes we use like 3 tensor products like back to back. So the question is like, do we do a fusion? When do we do a fusion? Does it make sense to do a fusion? And then the second sort of interesting thing is about just, yeah, different sparse storage formats. Like, because my tensor, like so far I can't directly map it onto like any sort of like the CSR CEO thing. And I know there's like a trade-off space between complete dense and then complete sparse. And my guys are like, I would say 5 to 10% sparsity. So it's in a very like awkward sort of regime. But yeah, I'm happy to hear your thoughts on that. And I think, yeah, this is actually my last slide. I was like literally hoping that people would start like bashing me with questions by the time I reach the end. But yeah, thank you.
Thank you. Moving on with the nice presentation, all this into one, and I think we only